So, for the Kennedy's theory, based on the channel design, I can take the first case as the given is the discharge Q, rugosity coefficient N, and critical velocity ratio M, and side slope S. Okay. And the second case is the given is the discharge Q, rugosity coefficient N, critical velocity ratio M, and V by D ratio X. So before that, we'll see about this. Uh, I mean the non-silting and non-scoring velocity, uh, the critical velocity, which is related to the depth as VO. So here the critical velocity and the full supply depth is VO is equal to C into D power N. So it is found that C and N were 0.546 and 0.64 respectively. So we have the velocity, that is the critical velocity, and the full flow depth. Now VO is equal to 0.546 into D power 0.64. And again, they realized that the critical velocity was affected by the grade of silt. So they introduced another factor M, so which is the known as the critical velocity ratio CVR. So here the critical velocity ratio CVR is the VO is equal to 0.546 into M into D power 0.64. Okay, so now the Kennedy introduced a critical velocity ratio M based on the silt grade, as M is equal to V by V divided by O. So, yeah. So M is equal to V divided by VO, right? And the M varies from 1 to 1.3, right? So the mean velocity is given as 0.546 into D power 0.64, right? So I'll tell you about this formula later on, because the Kennedy designed the channel is based on the available ground slope and the suitable B by D, that is the bed width to depth ratio, was fixed by the experience. So Kennedy used the Cutter's formula for velocity, right? So as I said in the case one, so for the case one, the given is discharge Q, rugosity coefficient N, critical velocity ratio M, and bed slope. Yes. So first one, they have assumed a trial value for the depth D in terms of meter and calculated the velocity from VO is equal to 0.546 into D power 0.64. And the area of cross section from A is equal to the area of cross section. So that is A is equal to BD plus D square divided by 2, right? So the area of a section is calculated by A is equal to BD plus D square by 2. And also assume a side slope of half is to 1 ratio. So side slope as half is to 1. And the and it is said to calculate the base width of the channel from the area. So the area of the session. So that is A is equal to BD plus D square by 2. And now you can find the vectored perimeter. So how will you find the vectored perimeter? So I hope you remember. So that is a P is equal to B plus D root of root of what? So I hope you remember how you used to calculate the wetted perimeter. So you can tell me what the root of, okay, and post it in the classroom section by I mean when you see this, okay. So and then hydraulic mean depth. So you know about the hydraulic mean depth, that is A by P, right? So hydraulic mean depth. So that is cross-sectional area of flow divided by the wetted perimeter. And finally, you can calculate the velocity from Cutter's equation and compare with the assumed value. Now, the second one is the given discharge Q rigorosity coefficient in critical velocity ratio M and B by D ratio X. So for this case too, what we have is we can calculate the velocity from the previous one, that is V is equal to 0.546 into M into D power 0.64. And also you can calculate I mean you can calculate your area with A is equal to BD plus D square by 2, right? So keep in mind to take care of the B by D ratio. X is there, right? So and also you can have the Q. So find the Q value. So you can arrive it from Q is equal to A into V. That is a continuity equation. And you can find the depth. So from the depth, you can find the bed width and the hydraulic mean depth, right? And then you can use the bed slope from the Cutter's equation and you can go ahead. So these two uh, samples and criteria were there. So here we have the values of C, that is for the types of material and other aspects, and also the types of silt and the value of M. So these are the expressions adopted for the Kennedy design, Cutter's formula, Manning's formula, and Chess's formula. You would have come across all these things from fluid mechanics, hydraulics, and even in environmental engineering, right? So we are going to use the same formulas, the Cutter's formula, Manning's formula, and Chess's formula in the canal sessions also. So here the Kennedy haven't given any kind of equation for the slope of the canal. Uh, so you can plot it and So you can always plot it with a certain range of slope, which you get it along with the alignment, longitudinal slope, and with that you can have a note of it. So for here, for example, they have given q is equal to q to cubic centimeter, and n is equal to the certain value, and m is equal to certain value, and with that they have got the various slopes, that is 1 in 5,000, 4,000, and 2,000. So with these aspects, and so some guides to be followed out to choose the B by D ratio. So I already shown the calculating and fixation of the B by D ratio, that is with the Woods formula, right? So Woods normal design table, they have used it, and to find the and to have the nominal fixation of the B by D ratio. And for this, the empirical formula for the table for B by D ratio is given here. So that is D is equal to 0.5 root of B, and also that you're having that empirical recommendations for the water depth of discharge and the depth in meters. And so as I shown earlier about the uh, continuous equation, the Cutter's equation, and the Kennedy's equations. Yeah, you can also use this 0.55 instead of which I have already shown you, that 0.546. Okay, and these are the recommended values from the Indian Standard of Ergosity Coefficient N from the IS code 7112 1973. Here we have some various kinds of nature of the channel surfaces and also the values. So as I said earlier, with the design procedure, so the first one that's given is the Q, N, M, and the S for the L section. So you can have the trial, you can assume the trial D and then calculate the velocity VO, and get the value or the area with the continuity equations, or you can use that area of area, how to calculate the area, which I have already given you. And also by knowing the A, D, and A, calculate the B from the geometry of the canal section. And then you can also find the slope of the canal if it is in case of aluminum oil, which is half is to 1, and A is equal to B, D plus D square by 2, right? So from this, you can find B and also calculate the wetted perimeter and the hydraulic mean depth of the following, right? So here you have the wetted perimeter, and you can use it. You can find the hydraulic uh, mean depth. And then you can calculate the actual mean of the velocity of a V from the Cutter's equation formula and compare it and get the statement. And the second one is the same thing, but the given is a Q, N, M, and B by D ratio. So you have to include B by D from the Woods table, and you can take it in form of X and incorporate in the area values, and you can follow the procedure, right? So in the discharge they have in the area, they have included. So design an irrigation channel on a Kennedy theory to carry a discharge of 45 cubic. Take n is equal to 0.0225 and m is equal to 1.05. This channel has a bed slope of 1 in 5,000. So as I said earlier, first you have to assume the depth. Let's assume d is equal to 2 meter, and you can use the velocity critical velocity formula. V is equal to 0.55 m d power 0.64, sorry, d power 0.64, and you can find the value in terms of meter per second. And next you have to find your you're going to use your continuity equation and find the area. And because here they have given the discharge, so you can use the continuity equation and directly can find the discharge, right? I mean, the area, because velocity also we found, right? And now with the trapezoidal sections, you can use a half is to 1 slide slope, and you can use the formula and find the value of b. Now with that you can find perimeter and followed by the hydraulic mean depth, and then you can use the Cutter's formula and get the value of v. So in order to increase VO, you increase the value of D. So here the expected range is less, so you are increasing the D value, and again you have to proceed the same. See the two ratios, more or less one, the ratio of two velocities. So hence no need. But in case of examination, if you are going to have a wrong trial or something, then in that case, that if you are not getting the same kind of a thing, I mean a feasible depth, then you can stop it wherever you did, and you can write that further trial to be necessary in order to make the depth or the dimensions feasible, so you can have the further more trial. Likewise, if you have no time, then also it's okay. So next we have the design an irrigation canal to carry a discharge of 14 cubics. Assume n is equal to 0.0224, m is equal to 1, and b by d is equal to 5.7. So again you can find the b by d, and here b by d they have given, so no need of use of any kind of table here, and you can use that ratio, and you can get the terms b by d you have incorporated inside, and followed by you are using you are finding that VO, and finding discharge, that as the discharge is already given, so you're going to incorporate the discharge and going to find the D, so that you can get the value of B, and then hydraulic mean depth, and also followed by the Cutter's formula, and you can find the slope, because we need slope, right? So also you can use the trial and error methods to find the to get the feasible slope if possible, right? Because that's a method, you have to use the trial and error to get the feasible slope, yeah. And so if you uh, think of drawbacks of Kennedy's theories, then that is importance of b by d ratio was not noticed, and the slope equation was also not given. Silt concentration and bed loads were not counted, and also the silt grade was not defined. So these are the several issues we have encountered with Kennedy's theory, Mostly that is based on the trial and error. So you can use this for a tutorial and get the values, and you can submit it in the classroom. So you can pass the video and try to complete it. And if you don't know properly, then you can go ahead and watch the video. So find the maximum discharge through an irrigation channel having the bed width 4 meter and fully supply depth is 1.50 meter. Given that n is equal to 0.02, s is equal to 0.0002, slide slope 1 is to 1. Assume reasonable data if necessary. Comment whether the channel will be in scarring or silting. So here again, you have N, D, and S. We have, so you can find the cross-sectional area, and then you can go ahead with the finding wetted perimeter so that you can get the hydraulic mean depth. And next you can get the you can use the Manning's formula and find the velocity. And when you find the velocity, you can use the continuity equation and find the discharge. So you can use the again velocity formula, and you can go ahead with the Kennedy's formula. CVR, the mean value, the mean velocity by Chess's formula. So you can find the values and make sure that the V and VO should be having 1. So if it gets 1, then it is perfect and non-scoring and non-silting. So if you are getting a less than or a greater than, then you have to revise it. So as I have already shown you in one particular example, right? So see the example. So here it's more or less 1. So we have stopped the trial here. So here it's not like that, right? So you are choosing another value and going ahead with the problem, right? So choose accordingly. Whatever you're going to choose, let it be a little bit high worth so that you will be getting it in the first uh, trial itself. Okay, so that's all for this session.